Excellent.
So I'm very excited to introduce a very exciting speaker, and I can tell you, Lyle, I attended a seminar or workshop with him last year, and you can certainly not find a speaker as exciting as Lyle. So Dr. Lyle Ungar from UPenn, a very interesting career. Lyle is actually a chemical engineer, and with a BS from Stanford and a PhD from MIT, and he actually got tenure as a chemical engineer. And after that, he decided that it's more fun playing with machine learning, natural language processing and understanding, and data analytics and data mining and so on, and behavioral modeling, that catalysis doesn't excite him as much.
I never did catalysis, materials, fluid dynamics.
And all that stuff, it's not so exciting. So he switched departments and he became a professor with computer science at UPenn, and he's there since then. He's working extensively with many of the Department of Defense funding agencies for his projects, and we all know that machine learning and data analytics is a big deal right now. Has many students who work with Google, so be prepared for a very exciting, adventurous seminar on machine learning with the title of Deep Learning and its impact on engineering. So thank you very much for being here, and thank you all for attending this seminar.
Oh, thank you. I hope I can live up to the hype and the pitch, which is probably typical of deep learning, which is all about hype and pitch. So I want to give a slightly unusual lecture maybe, and feel free to interrupt, which you will do. If we don't get to all the slides, it's okay. But I've noticed there's been a huge change in the world, which is affecting all of us. I was trained as a modeler, how to write down conservation of energy in physics and chemistry, and write down equations. I moved to computer science, and we trained to write programs to tell computers what to do. And the last few years, there's been a rapid shift using mostly decades-old technology, we can talk about how it changed, to not telling computers this is the model, this is the physics, this is the chemistry, but to give them examples where they learn only based on, here's an example of something, here's a label, here's a controller for a video game, learn to play the video game. No instructions, no coding. So training computers not by telling them the models or the programming, but by giving them examples. What I will mostly do is talk very little about engineering, but we'll come back at the end and talk about it, and talk about what's already happened, in the sense of what's happening at places like Amazon and Google and Facebook, where most of my students end up, and then sort of look at what that may mean in terms of how engineering is done. Cool? Cool. Okay. So, I probably don't need, anybody not seen something on deep learning? Right, so machine learning, face recognition, object recognition, self-driving cars, not here yet, but lots of money going in. Any speech recognition. 5 years ago, if you used a phone and talked to it, used a hidden Markov model. They're now 100% deep learning based. Works better. Still crappy, but much better. Machine translation. 3 years ago, if you went to Google Translate and typed something in English and translated it to Chinese, it had a whole bunch of computational linguistic rules for translation by programming. Now it's end-to-end deep learning. It's a neural net, takes in English, puts out Chinese, mostly not very good Chinese, but better than my Chinese. And this is happening in lots of places, somewhat less in engineering, but we'll sort of see maybe later where that's going. Lots of people doing claims on the business side. Big data will become a key basis of competition. Might not have all the jargon things. Or my favorite, Harvard Business Review said that data science is the sexiest job of the 21st. I've never been called sexy before. Didn't even know I was a data scientist. Okay, so lots of hype. And the question is sort of maybe what's different now than I was doing neural nets in the 80s. And a lot of technology looks pretty similar, but it didn't change the world then. Whereas now there seem to be a few billion-dollar companies that are investing rather heavily in this area. So I'm going to argue, sort of trivially, that almost all of machine learning is just optimization. You take in some X, a description of your plant or your image or the sound into your microphone, and you have some parameters theta in some fancy model F, and you put some Y as output, which is the label, like the words, or whether this is my face or your face or a dog or a cat. And you want to minimize something that makes the predicted y look like the actual y, like some measure of loss, right? Squared error, loss was historic, now it's more log likelihood, but we're quibbling. That's it. That's all of machine learning. It's sort of trivial. On the other hand, companies like Google are spending $1 billion getting better at this. So there's something else going on, and machine translation didn't work 2 years ago with this. It does now. So that's sort of want to explore a little bit of what this is used for. What's new about this? A little bit different loss functions, trying to get nicer measures of what it means to have the right classification error. A little better optimization, we'll cover them quickly, but it's basically stochastic gradient descent. That's very different from what it was 20 years ago. Much nice flexible models, literally a million adjustable parameters to fit things, and lots of compute power. Right? And in some sense, arguably, again, feel free to interrupt with questions. I will read occasionally, let people ask questions.
Also, you have this
Yeah.
dropout and so on.
We'll talk about dropout, we'll mention some of these other methods of doing regularization. They're part of, the strategy is take an incredibly flexible model form and then regularize it, do something that constrains it to make it so it doesn't overfit too much. And it's
Also big
all
data.
black magic
Also data, I would say.
and lots of data. But in some sense, there's a classic thing which I stole the core from, that's more of it. 1900 to 2000, you can look at the millions of instructions per second you can buy for $1,000 on a exponential k, a billionth, a millionth, 1,000. You can look at the early physical calculators. You can look at the vacuum tubes. There's ENIAC from Penn, my university, back here, about 45. You can look at computer chips, integrated circuits, and people have said correctly that Moore's law has ended. The old-fashioned Moore's law has ended. But I took Hans's old slides and I looked up compute power per dollar from some modern computers, like an Xbox and a PlayStation, which are important because they use graphical processing units, which is what all of the deep learning stuff uses. And what you can see is that they're still beautifully going up on that same trend in terms of calculations per dollar, going up wonderfully. So the number of components of integrated circuit per square centimeter is totally maxed out many years ago, but the computation power is still going up exponentially. In some sense, that's the whole story and what's happened. And the dropout is nice, but if you don't do dropout, there are a bunch of other methods that still work fine. Cool. Power changes the world. Oh, just for fun, you can look at where we're sitting. We're sitting around the CPU power of a mouse or a monkey now for $1,000. So I can look at how much CPU power, GPU power Google has compared to this room. More, actually. So you need to have something of order 1,000 laptops to meet the GPU power, CPU power of a brain. And 1,000 laptops is not that much for Google's got millions of times that compute power, just to give a flavor of these things. So there's lots of power out there to computing. But everything I'll show you is still doing fairly small calculations, say, compared to what a human has in terms of compute power. That's a different topic. So why does this work? Lots of data. And I like sort of a graphical illustration, which I've stolen from Hayes and Efros. Here's the game. You take an image, a random image off the web, you delete some piece of it, and try to reconstruct the missing part by taking other images off the web. And it turns out that if you go out there and look, you can find the most similar images, some similarity and then you can then interpolate a clever little bit of math to do the smoothing so the boundaries aren't there, and you fill in the missing piece. And it works embarrassingly well, partly because most images are of things where there are other images of, right? Picture of the Eiffel Tower, the Sydney Opera House. If you delete half of the Eiffel Tower, there's lots of pictures of the other half there. But this is also true of most of chemical plants and aircraft flying or whatever else you're modeling. Most minutes look like other minutes, most of the things you're modeling are the things that are there, and these systems tend to work on average spectacularly well. Now, as a minor detail, but if you're concerned about the one thing in 10,000, yeah, okay, my thing only crashes one time every 10,000 minutes, you know, it's not so bad. So they tend to work great wherever there's data, and often there's amazing amounts of data, but they tend to fail in rather unexpected ways on the rare cases. And of course, they're always rare cases. No, that's on the downside. Cool.
Important things are the variables.
Yeah, important things are other rare events. Maybe, maybe not. Google has made billions of dollars. How accurate are they in finding the thing you want? There used to be an I'm feeling lucky button that would actually give it. I don't notice that Google gives me a single return in general. They're wrong most of the time, and they're incredibly useful, right? So I think the question is where these things, there are an awful lot of cases in the world where if you're wrong most of the time it's still useful. If you are running a supermarket and you want to know how much ice cream should be delivered from the truck next Tuesday, it's fine to be wrong. You can have a positive and negative loss function, over-ordering, under-ordering, and a good forecasting algorithm can save you, okay, a few pennies per week on the storage of the ice cream, which if you do that over 40,000 items starts to add up to a competitive and very thin industry. So a lot of things it's okay to be wrong a lot. So these things are all used where it's okay to be wrong.
I mean, you're so totally inefficient before, that's right.
And most things are incredibly inefficient.
Right.
You were old enough to remember before you could use Google search to find things. You had to walk to a library and open a paper book and read through it. Google's much faster than that looking inside the book, right? So yeah, sure, you were totally inefficient before. Now you're only sort of inefficient. Okay, so I want to show 4 examples, classic sorts of things. Take as input a web page and an ad. Google has a lot of web pages and a lot of ads. Will you click or not? Are they right? I know they're mostly wrong. Click-through rates are maybe 1 or 2%. What have you bought in the past? What's your expected discounted cash flow, net present value? Facebook posts, who are you? What's your age? What's your sex? What's your personality? All these things can be shown with lots of error, but in ways that are massively useful. And I'll show a few of them just for fun. I mostly do language. I couldn't originally one. These are words most predictive, most correlated with male or female? Female. Note what a word is. I'm a statistician. Things like my hair, love you, are things that co-occur. Yay. You old guys know what this thing is? Heart. Very good. Okay. Just checking here. You get, husband and boyfriend and lots of pieces there. We can tell about 92% accurately whether someone's male or female by their language. It's incredibly cliche. Before you're embarrassed that I'm insulting females, I will show the male one as well. I'm not sure I want to do this, but trigger warning. In defense of these are, all I can say is this is the data. I'm a statistician. These are the words most correlated with being male in America about 4 years ago on Facebook. In defense of my sex, it's not all bad. We talk a little bit on average more about beards and governments. And interestingly, men tend to talk more about my girlfriend, and somewhere is my wife, whereas women tend to talk about husband or boyfriend. So men tend statistically talk a lot more only about their girlfriends, whereas women talk about their boyfriends and other people's boyfriends as well. You may judge whether that's good or bad. I sort of wish I was a woman, but okay. Anyway, what's the relevance of this? The relevance is, first of all, that there are lots of features. I put 40,000 words in this regression.
Why are they talking about India?
Why did I have in India? Almost all of the location ones are sports. So things like the World Cup. And I don't know what was happening in this particular time about India, but something either political or sports.
Not very on the south.
Brazil and Germany, I can tell you, because this era was in fact a couple soccer games that people were watching. So I don't know what India was doing at the time. We'll go back and look. So what do we see? First of all, if you throw in lots of features into a model, you will select statistically a small number, thousands, but I've shown 100 or so, that are highly correlated and predictive. They're errorful, which is 92% accurate, so 8% of the time I'm wrong about guessing whether they're male or female. It's still useful for people trying to target stuff. Sometimes giving some insight. I pick words to start with that's easy to interpret them. We all at least have some intuition of what it means to be male or female in the US and what things talk about. And that's sort of a lot of the machine learning is grab a very rich feature set, throw it in with a lot of data. This is 70,000 people behind this. 70,000 people shared between their Facebook posts and their age and sex and a bunch of other stuff. And build models. Cool. People are doing these now for biopsy. The latest results show that we're trying to recognize, anybody has cancerous or not? Same accuracy as well-trained doctors from automatics. You've all seen some versions of image and recognizing what's it called? A sedan, sorry. A bicycle. What's in the images. If you haven't tried machine learning, or tried to do machine translation, type in a word. They're mostly pretty crappy. Instead, pretty good for close languages, English to Spanish or German, are fairly accurate. If you go to Chinese, I'm told they're pretty bad, but still extremely useful and rapidly getting better. So what is it? There is some nonlinear function that maps from any English sentence to any Arabic sentence. It's just an equation. Trying to write that equation from first principles, really hard. Many linguists have spent many decades trying to write that functional form. Of course, there are a bunch of languages, each have different equation mapping them. Turns out it's really hard to write the equations that map from one language to another. Most of you who learn a second language, there are so many things, for example, in English that are just bizarre, right? Don't make any sense, you just have to memorize them. What do you do? Can you put out a light? Can you make out a light? Can you turn out a light? Can you push out a light? Depends which language you're speaking. Those work in some language, right? So you gotta memorize it. So a lot of these are learning nonlinear functions of some form, and in general it's proved in the case that if you have a lot of data, it's much more accurate to learn the nonlinear function over a huge class of functions rather than pay some engineer to figure out the right equation. Is this relevant for you guys? You're mostly in the business of writing down the right equation, right? You're being trained well on how to write down the right equation. And I'm saying, all these deep learning guys are saying, that's great. If you've got no data, we'll hire you. If we don't, we can just find a lot of examples and the computer will learn the right equation. And get rid of you guys. Or put you on something different. I am worried about people losing their jobs, but I'm mostly worried about sales clerks and truck drivers. You guys are all going to get jobs. You'll just use these tools. So I'm not particularly worried about unemployment among engineers. Last I checked, the job market was pretty good. Especially if you can use these tools as part of your toolkit. But it is replacing chunks of that in many other fields. Cool. What are these things? They're just either non-parametric models or semi-parametric models, models with typically tens of thousands to tens of millions of adjustable parameters, incredible flexible form, something where you got to have a lot of data. If you're going to fit 1 million adjustable parameters, it'd be nice if you guys say 1 million labeled data points. My rule is always 1-to-1 works well for parameters or things you fit, which makes life hard. So a lot of stuff it's hard to get 1 million labeled examples, but there are ways to cheat. We may talk about some of those. And currently, very trendy, of course, deep networks where you have something learning representations, feature recognizers. There will be some of these going I'm going to talk mostly about supervised learning, jargon where you have some X as input and some Y as a label you're learning. There are a bunch of unsupervised ones that look like this for what analysis, but non-linear, instead of doing a linear form. And we'll talk very briefly about reinforcement learning. In a lot of optimization problems or control theory, you don't have an input and a target label. You're trying to pick some control action that maximizes some utility or minimizes some cost. And these things then do a successive gradient approximation that says, keep mucking with the control action until you can keep getting higher in whatever performance. We'll talk very briefly at the end if there's time for probably about these. Good? Good. I have to be obligatory. Here's a neuron schematically done with inputs, and here's what happens. You do a spike in the change in the voltage, you get the current, in this case, you get a spike in voltage. These artificial neural networks are incredibly, vaguely, sort of, kind of, a little bit modified after the neurons, but in fact, mostly people don't worry at all about the inspiration anymore, so the artificial neural network's a bit of a misnomer. What they have is some nonlinear function that takes a bunch of inputs, the x's, multiplies each by a weight, adds them up. If you then fit them, that'd be linear regression. You then pass them through some nonlinear function, like a logistic function, that'd be logistic regression, and then you can fit that so one neuron looks like a simple regression with a nonlinear transformation. Typical ones people use historically was 1/1 plus e to the minus sum of the weights times the inputs. A fine function, nothing magical about it, sort of pretty. But people love to draw pictures, right? Here's my pixels, here's my temperatures, so my pressures, multiply by a weight. But what they then do is take a bunch of inputs, so we do, multiply them by weights, take the outputs, multiply each of those by weights, do a nonlinear transformation, keep repeating. What you get at the end of the day is something that picks weights, every line's a weight, to try and make the output as close as possible to the label for a bunch of inputs. What that does at the levels builds sort of feature detectors. In the good old days, people like in image recognition spent lots of time building definitions of features. Wavelets and Haar basis functions and Hog features and all, I don't know, I'm not a vision guy. They're all out of business. Rather than figuring out a clever way to combine the raw inputs into some sort of a feature, some combination, the computer finds an optimal way to do it. Optimal in the sense that it minimizes some loss function. Question? Makes sense? Nothing. There's nothing there. But you do more layers, right? Deeper, deeper. So you have features of features of features. What do? They typically map some input. These are used a lot successfully currently in anything that's perception-based, sound or speech. An image of an object to what it is. An image of a person to who it is, like Facebook. You'll see, shows who you are. A picture to a caption describing it. A board position on a game to probability of winning. Word to a sound to a word. Right? All these are just some input mapped to some output with some incredible general nonlinear function. It's embarrassingly trivial, actually, when you get to it. Where's the science? I don't know. But how does it work? So classic early days ones, people took a bunch of images, typical, get a flavor for the size of these. Early ones were 50,000 images. Images look like this. And the labels are, that's a 7, that's a 5, that's a 5, that's a 9, that's a 0, that's a 6. Looking back in the late 90s, people used k-nearest neighbors or radial basis functions and got a 5 or 3% error rate. In sort of modern versions, people then shifted eventually, I'll skip the sport vector machines, to the first neural networks of the modern era. They're getting from 5% down to 0.8%. The current ones are getting 0.2%. Is like one wrong in the whole set. What is it learning? Just a mapping from each of these 28 by 28 images to a label. But big gains. Now Google has cool modern versions of these, bigger data set, 600,000 in typical modern training set. What they have are pictures of house numbers. That one is a 65, that one 16 probably, that one 27, 271 actually. Okay, and if you look at the early versions where people were doing cleverly handed, early being 2011, I won't give you a time frame of these things, people doing cleverly engineered features, they're getting 36 down to 15% error rate to get the whole numbers right. K-nearest neighbors, find the most similar ones, is getting 9%. By 2013, they're getting down to 2.5%. Humans are at 2%. The recent ones, 2015, just slightly superhuman ability. Right? Turns out also, you ever do these CAPTCHAs, prove that you're not a computer? use this exact same software, can solve CAPTCHAs too. Google was not interested in breaking CAPTCHAs. They were interested in having the Google Maps be able to read house numbers. But they solved CAPTCHAs as a side effect. Because it's able to take distorted things. And they're funny. These are, some of these are hard, well, 38, they're angles, you know. So what are you getting on a fairly simple task with 600,000 examples? You can actually get slightly superhuman performance. How do you label these? It's always the trick. It's mostly not crowdsourced. In fact, what Google does is they have a bunch of trucks that drive around the world, taking videos of things. And as they take the pictures, in many cities, in many parts of the world, it's 24, 26, 28, 30, 32. So the house numbers are often quite well done. People sometimes tell the address of where they live as their home address, which they're choosing from their phone with an exact GPS location. Some of them are easy to recognize because they're clean numbers. So almost all these are done by, we know that that was 14, we know that was 18. The one we can't tell is probably 16. So they're interpolating physically. Other places, things are weird and they can use this for places that don't fit up the regular pattern.
Well, the images that you started was a crowdsourcing. They had from Caltech.
No, these images are, these
This is the Google stuff.
the other ones are crowdsourced. These ones are actually from Google proprietary. This is from Google Street View. These are Google proprietary images that I'm showing here. They're not crowdsourced. They're taken by a large company with lots of money. Then people started doing images, recognized as an early one with 50,000 images of, in each of 100 categories, horses and boats and cars and airplane. And you can see a similar pattern of the error going down systematically, rather more slowly with pieces.
So what is the problem here?
The problem here is given an image,
No, I'm.
what, yeah, what's the problem?
Never.
Why is it not perfect?
Yeah, why is it so bad?
Why is it so bad? Well, look at, for example, the ships. Can you write an equation that describes what a ship looks like?
No, I'm not asking that question.
Yeah, okay.
I'm asking is, how well do the humans do on this one?
At this level, 2015, these are still well subhuman.
Yeah.
But we'll get there. We'll get to human level performance and other ones. And so the classic breakthrough came with Jeff Hinton in 2012. Again, to put dates on, I feel like giving an ancient history lesson, I'm sorry, but you know. 2012 was the classic modern breakthrough, and I want to actually go through and give a big chunk of his talk, which will take 5 minutes, to actually show what he did to give sort of the first really successful one. He was at the University of Toronto, still is sort of, but now he's actually mostly within Google, where the money is and the big GPU power. One thing he did is instead of using a logistic or a hyperbolic tangent, he said, oh, we can do a nonlinear transformation that's just, the fancy word is a rectified linear unit. It just says, take the weights times the x's, sum them up. If it's negative, output 0. If it's positive, output the value. That's a nonlinear transformation. It's very fast, by the way, to compute the derivative of that function. Oh, but speed matters, right? This function, which is a hyperbolic tangent, computing the derivative requires many multiplications. This one requires a table lookup, a quick lookup. 1 bit. Is the leftmost bit 1 or 0? Is it positive or negative, right? So again, a cheap trick, but it gives you a factor of 1,000 speed up almost. So you take fast derivatives, and it has some nice features that this one tends to saturate, so the derivative goes to 0 when it gets very big or very big. Here the derivative goes to 0 here, but stays constant there, and that makes things converge sort of better in the optimization.
The derivative doesn't exist at that point.
The derivative does not exist at that point.
It's upgrading there.
Right.
There is, that's quite true. And does that bother Kinton? Not really. How often do you actually see a 0 within the middle of a neural net, which you have a bunch of real numbers being added and combined? You know, a big measure 0, I think is the technical term.
It's a stochastic gradient, so it's essentially can think of it as stochastic subgradients.
Yeah, exactly.
And another thing is, it's also convexifying the function too, because This is basically a idealization of the integration of the logistic.
It's an approximation of that. On the other hand,
So,
is the overall model convex when you combine all these?
no, but the thing
No,
is
it's
that
incredibly non-convex.
no, the logistic thing, the
Yeah.
second derivative can be negative. Whereas
Yeah.
this can never be,
Yep.
okay? Because it's an integration, so
So,
that's the major one.
nice trick. Not very deep, but it turns out these things work really well. These things work okay. If you want to be a mathematician, I can prove with either of these as basis functions combined over and over again. The trivial function theorem says, given enough of these things, or enough of these things, you can approximate any well-behaved function, arbitrarily well. But that theorem is useless, because you have to search to find the features that actually give you that combination. So yeah, they're arbitrary universal approximators. You've got enough of everything. Everything can be split up enough, you can approximate anything. Cool. Good. So what do? They take an image in, they pass it through 7 different layers. I showed you the combination of weights through a transformation. They do it 7 times. The first 5 of them are convolutional layers, which I'll show in a second, which is a nice way of building in certain invariances. I think if I were you guys trying to figure out how I could contribute to deep learning, it's what invariances can I build in? Conservation of energy, conservation of mass, continuity, bounded differentials, whatever it is you want to build in, and that's where actually physics still matters. And for images, it turns out there's some nice, simple invariances that work really well. And what they do, I'm not sure this picture is helpful, take a whole image, very blurry here, and for each little window of the image, have a mapping that goes to a hidden layer, and say, what I'm going to do for my feature detector is each little window, as I move the window across my image, will have the same weights, combining those to the features. So if I were looking for a cat or a dog or a border between an edge of a chair, it will look the same no matter where it is in the image. You with me? If you shift it across, shift it down, it's the same thing. And that means that rather than having a separate model from the 9 pixels here is from the 9 pixels here, it's the same function mapping that as a feature detector.
So what if you have a cat and a dog in a picture?
Well, what you're going to have is a whole bunch of these images, these sub-images, these little sub-windows. Each sub-window will have actually a whole battery of, call them filters, or call them weights. And effectively, it's looking in each of dozens of little sub-windows. Is there a cat there? Is there a dog there? Or at the low level, is there an edge there? Is there a bottom there?
So size of the convolution window is an arc. Picking the same.
And it is an arc, but they just pick several different sizes because it could be closer or farther away. And so it notes basically assumption is that there's something close to translational invariance across the image. They don't do is, what they could do is make it rotationally invariant. Why not? In an image recognition, why not say that whether the image here or whether it's there is the same? Most pictures of faces or cats, there isn't asymmetry across most photographs, right? We live in a gravity environment. Down and up really are distinguished. And if you look at most photos, if they're upside down, you can tell they're upside down, right? You could build in rotational invariance, but the world is not rotationally invariant. You with me? So this was tremendously important. Rather than finding the entire class of all functions from some set of pixels to labels, it's one that says assume that there's lots of little feature detectors at the low level, each of which is translationally invariant. And then those first level shallow features, which mostly detect edges, then get combined in a deeper layer of the network to find combinations or objects, which in a deeper layer and a deeper layer eventually detect cats and dogs and people. Clever, right? A little bit of invariance built in. They also do some local pooling. When they look, again the pictures won't help you, but when they look within one area, if they have a bunch of feature detectors, they will also compute sometimes the maximum of all the outputs of that measure. Which you can think of as, if we got a cat detector, if there's a cat here, or a cat here, or a cat here, we have a cat, right? So it's a max function. So the functions are just translational invariance and a periodic maxing of the outputs from some set of peaks in some region. And it uses the fact that pixels close to each other are correlated. Cats are not spread out across a little bit of a cat here, little cat here, little cat there. They tend to be physically contiguous. Right? So that piece of physics is built in.
Did they replace this recently with some routing something? Like,
There are many, many different architectures that have been done.
no,
Um,
November of this year actually.
Well,
Okay.
this year there are 3 or 4 of them. The classic ones here have an input where it takes these images, moves them 4x4, processes it, pools it, does it with the convolutional, then it has 2 dense layers. Now there are a lot of work on having, instead of having a strictly layered system, you can take each of these inputs here and send them all the way there. So you could do something like a highway network. There are dozens, no, hundreds of different architectures.
No, conceptually there was some recent thing that was done.
There's many conceptual ones. Kenton's current thing he's building on is capsules, so he assumes that there's
Capsule.
structures. So they don't work, but Hinton was like invented the whole field of deep learning, and he's way smarter than I am, so the fact that it's never worked, and he can't get his papers accepted because he has no results, he's still smarter than I am. But so the other theory, if you look at how human or cat retinas work, they're actual regions of vertical integration. So he has something that instead of having a feature detector for a scalar, has little chunks of these so-called neurons, which output vectors effectively. So instead of a scalar feature detector, it's a vector feature detector. It's a fancy different structure on it. It may in fact prove to be brilliant or maybe useless, I don't know. You know, Hinton's pushing it. Who might argue with Hinton? But I wouldn't use it today. If I were an engineer, I wouldn't bet against Hinton either. He's been right before. So yeah, capsules is another architecture. Assumes there's some sort of structure there. Clever. So these things get lots of adjustable weights inside them, but lots of them so-called tied. It's the same weights for this image, that image on the model. So what do you get? Something that ends up having 650,000 of these so-called neurons that take a weighted input and do a nonlinear transformation, 60 million parameters in this, and these are actually copied many times, so if you do all the copies of them, 630 million copies. This runs on, this is a small one, it's very old, right, 2012, runs on 2 GPUs for about a week. Results I won't show, one of my favorite breakthrough ones, Kwakla did one, the one that famously recognized cats unsupervised, like a PCA for finding cats and dogs and faces. And I calculate he used it at Google, enough energy in his calculations, which is the big cost of these calculations, right? The cost of computing is energy, not the hardware, to power San Francisco for a month. But Google has energy to burn, apparently. Cool. So, a lot of structure. The modern ones, people will do these that are 60 layers deep. And now they're trying, oh, we can redo the same, we're like 20 layers deep. So there's a huge industry in trying different structures, but they all have something of order 1 million, 10 million, 60 million parameters in it. And a lot of stochastic median descent to estimate them.
The recent one is 152 layers, right? For Microsoft.
There are whatever you want, people have done them. You want 100 deep? Fine. How much does it buy you? That much. Now people are actually doing other ways to shrink. If you want, we can talk at the end of how you could take these ones that are 100 layers deep and replace it with ones that are 5 layers deep and get just as good results.
Right.
So it's true. All these things are solved by basically gradient, stochastic gradient descent. The other trick is, if you want to fit these things, you need a lot of data. And so what they do is, when you have one image, so here's the original image, they take a sub-image and then do a whole bunch of sub-images, each shifted by a couple pixels over. So you shift a cat by 2 pixels, and every whisker is moved. It's a new image. So you can generate crap loads of new images by just shifting the original one a little bit this way, a little bit that way, a little bit this way. Do you think? Because having only 1 million labeled images is not nearly enough if you're fitting 60 million parameters. Cool. How will these work? In each case, I'm going to show a set of images. The true label, as given in the database, is here. That's a mite. You can see what the computer classifies it. It says it's almost certainly a mite, maybe a black widow. This one's a container ship. That's a motor scooter. That one's a leopard. Some small chance it's a jaguar. That one, the correct answer is grill. The computer thinks it's a convertible. The second answer is a grill. That one, the correct answer is mushroom. It's 50-50 agaric versus mushroom. Anybody know mushrooms? I'm not actually sure what the correct answer. This one, the correct answer is cherry, whereas the stupid computer thinks it's Dalmatian. And it got the Madagascar cat wrong. It actually thinks it's a squirrel monkey. You all know that's not a squirrel monkey, right? No? Okay. So, over a very wide range of images, this thing does pretty well. That one, the lens capsule, reflex camera, let's see other ones, chambered nautilus. Ah, there's a nice mistake. This thing, it thinks it's a cellular telephone, when in fact, the label thinks it's a tape player. Why does this incredibly smart network think that that is a cell phone?
Held next to a face.
It's held next to a face, and what is it trained on? It's a statistical method based on frequency, right? The loss is how often you're gonna write. The training data, taken mostly from YouTube images, does not have a lot of tape players, it does have a lot of cell phones, right? These things, the loss function does things that are more frequent are labeled the more frequent piece there, right? So occasionally it gets things arguably really stupidly wrong because that's what it's seen in the past.
Also, the way they evaluate it is using the top 5. As long as you're in the top 5,
You can validate the top 5, I can validate the top 1. I showed them the top 1. If you look at the top 1, 80% of the ones I showed here was the top 1,
Right.
which is pretty close to
But
performance you would get.
when they say that, hey, I'm 98%, 99%, yeah, they're actually doing the top 5.
It's hard, and you're gonna quibble, you know, is that a reflex camera or a Polaroid camera? Okay, some of them it's weird, but it's clearly a slug and not a zucchini. And that's clearly a hen and not a cock, right? Which is a male word. You can, those of you who are urban like me, you know, the hens do look different.
I know those.
You can also do these by searching across within images, and you can find, for example, a Scottish deerhound. That's out of my ability, but it is correct within an image, or actually it got the sturgeon wrong. I thought it was a turtle. But the motors find objects within images. So, cool. Once you have these, you have a mapping that takes any image and maps it to a vector, which you can then use, take instead of the output, which is the prediction, you can take something which is the penultimate layer, the one right before the end, which is a set of features that are about to be converted to prediction. You can compare those against other images. You can take a query image, take this image, map it to this latent space, which is the next to last layer outputs, and then you can find other images that are close. Within this latent space, similar images are very close. Note that if you were in pixel space, it's pretty far from this image to that image. Most of the pixels are different. It's learned a nonlinear mapping that in some sense captures purple flower or white t-shirt or elephant, right? And these are sort of different elephants, right? And this is one mapping, right? Takes an image, maps it to a state, or a hidden state, if you will, representation, feature vector. Make sense? Works amazingly well, right? So you can do these. Google now uses these, and you can search for meal, and it will find that's a meal and that's a meal. They don't look very close in pixel space, but they're reasonably close in the neural net representation space. Sometimes they make sensible errors. That is called a snake, whereas where I'm from in California, it's called a banana slug. Right? You see Santa Cruz mascot. And it thinks that one's a dog. Which, okay, the resolution is not great, but what do you call the donkey mark?
Why is it a sensible error, the one on the right?
Because that, why is it, at least it's an animal, it's got faces, got ears, dogs are more frequent than donkeys. It's not like completely insanely stupid. So some of the errors you look at and you say, okay, you know, a 3-year-old who'd never seen a banana slug might call that a snake. A 3-year-old might call that a dog. But there are other mistakes that just seem incomprehensible. Now use for image search, you can type in statue to Google and it will find statues, things that are close to other statues in the space. You can type in sea and it will find other things where the images are very different, but the underlying representation is very close. Oddly enough, you can type in drawing and it finds drawings. You can type in Yoda and it finds not just things that look like the movie Yoda, but things that are in very different media, that look very different on a surface structure. So it's finding something somewhat deep about the structure of images, not just superficial. Cool. What do people now? They tend to use these rectified linear units, flat, and not the old-fashioned sigmoids. They're pretty, work better. They tend to use often log likelihood loss functions rather than squared error. They can be very deep.
Cross entropy, which is
Cross entropy. There are a bunch of other loss functions that look sort of like some version of a log of probability, right? Cross entropy, log likelihood. We're talking logs of probabilities, right? The correct space always of probabilities is log of probability, which you can call it entropy, or you can call it entropy. They tend to be solved with a mini batch gradient descent. You take, rather than updating after every single image, which is expensive, or rather than taking all the images, they'll take probably 50 or so XY pairs, compute one piece of gradient, often numerically, update the weights, take the next 50 observations, compute the gradient, repeat. That seems to work by far the best. Everybody uses mini batch gradient descent. They have typically 4 or 5 different regularizers, almost always a squared error penalty on the weights to keep them smaller, or a statistician called a ridge penalty. Dropout, which I'll cover in a second. Typically partial convergence. Nobody tries to find the global optimum. A, it's NP hard, and B, if you found the global optimum, you'd have overfit tremendously. Right? So I've got 60 million parameters, only a million images. I can't fit the data perfectly. If I do, I will actually have memorized it, which is useless. Right? So these things all about regularization, and typically lots of empirical things. I got to
what is this adversarial training idea about?
Adversarial training is a different version, very trendy for a generative model, a probabilistic model. You have one image, one network that tries to generate images, say, and a second network that tries to distinguish, is the image a real image or a generated image? And so the combined joint optimization then says the generation one should be such that the distinguishing one can't classify is it real or not. If it can't tell them apart, you built a good generative model, which is just to say a probabilistic distribution, over actual real images. So at convergence, and they're a little flaky to converge, at convergence, you've now learned a generative function that generates images that are indistinguishable as if they had been real images from some distribution, but it's a really complicated one, over all possible images. And the distinguishing one, which is a classic one like I showed you, says, is it real or is it fake? If this one can fool it, it's very good. So it's a nice way to generate probability models over something. How would you write the probability distribution over images of sea turtles? It's not quite clear again what the right equation is. Make sense? Dropout. I got to do dropout. So, get this nice network. You randomly remove half of the links or the nodes. So you have a network that's got half the weights temporarily zeroed out. You do a mini batch gradient descent, train it a little bit, then you put back in the ones you removed and randomly remove half again. Right? Sampling with replacement. You randomly pick a different half each time, right? A different random half of it, and you keep doing that until you get tired, usually not till convergence. In theory, this is sampling over exponentially many combinations of networks. Don't ask me to try and explain the math. It certainly means you're not stuck at local optimum, because you're each time solving a really different question. At the end of the day, you've estimated weights on every convection. With me so far? And then for the final network, use all the weights, but you have to make each of them half as big. So you have twice as many weights as you had before. And that's it. This is magic. It's very trendy right now. 3 years ago, no one used it. 3 years from now, I don't know. The latest talk I saw last month, instead of dropping out random half, they take a network that's 20 layers deep, and they drop out entire layers.
That makes sense too.
and randomly search over dropping out whole layers. These are just much smaller networks, much more efficient, much better conversion. So there's a whole world of trying to find clever search techniques and regularization techniques. It's hard to overfit quite as well when you got half the things thrown out every single time. Right? Other people inject noise into the system, that's a regularizer. Add random noise to the observations, add random noise in the middle. All these things do some
That was
sort
there
of
since
smoothing.
90s though. Adding noise was there for a long time.
Absolutely. Most of these things have been there since the 90s. But the GPUs have not been so good in the 90s. GPUs are much faster now than the 90s. I can almost remember the 90s. It was slow. Right? And again, the speed thing. I did my PhD thesis on cybers and crays. The Cray computer I had to stay up nights to use. This was a $30 million ton machine. It has roughly the CPU power of an Android telephone today, or an iPhone. Sitting here waiting for my texts is the whole Cray computer that I stayed up at night to use because it was cheaper at night. Cheap advisor couldn't buy me hours of time during the day. Right? So yes, all of it's old and some of it's sort of new.
So what do they do when they remove the entire layer? Just they disconnect up this
They
thing
just
like-
directly connect as a pass-through.
Okay.
Yeah. Cool. I think I'm going to skip a couple of these. You can tell if your data are straight, and there are other pieces there. Recurrent neural networks, generalized hidden, people have hidden Markov models, especially some of the Kalman filters. Just basically picture yourself with a non-linear Kalman filter, or extended Kalman filter, a non-linear hidden Markov model, and these then tend to take something which takes a sequence, say, of words. At each point, estimates a hidden state. At the end of the sentence, you have a vector, so you learn a mapping from an arbitrary length sequence to some vector. And then from that vector, you can map to something else, say, a French sentence. And given this one, we then map to a different decoder. The encoder takes a sequence of words, builds up a hidden state, and the hidden state is filled to a decoder, which takes it at each point, produces a word, and given that word and the updated hidden state, produces the next word. So you have an encoder-decoder system, one that does from English to word, one that does from word to French. That's how machine translation works these days. Very cool. You can do it for a chatbot. Take a question, decode it to a vector to an answer. Works sort of. I won't show it. You can take as input an image, encode the image to a vector, and then feed that to a decoder. You can get a language description of an image. Right? Just a nonlinear mapping. How well does it work? Some of them are astounding. Some of them are less astounding. A man flying through the air while riding a snowboard. Well, what do you see? You see it's clearly through the air. I see a face, and apparently in the training set, the most common thing that you saw flying through the air with maybe a face on it was a snowboard. Again, when they work, they're unbelievably good, 2 pizzas on the stovetop, and when they fail, they're unbelievably bad. Because it's hard to picture this nonlinear space and what's happening there. Finally, I want to talk about reinforcement learning, because I think that's a lot of control theory. Google has famously trained a lot of models that you have some sequence of actions, say playing a board game like Go, and at the end or some period you get a loss or reward, like winning or losing by a certain number of points, and at each point you choose a control action, in this case where to play on your grid of stones, and you're never told what action you should have taken. All you do is you take an action, the environment takes an action, you take an action, the environment takes an action, and after a certain number of moves, you get back a reward. And with a lot of GPU power, you can learn to beat the world's best human at playing this game. Cool, you've probably seen the announcements of that one. Similarly, they've done video games, given nothing more than the pixels being displayed in the video game and the control actions. Keep randomly doing control actions until you actually learn one that wins the game. You get human level gaming performance on Atari type games just by doing stochastic gradient descent methods in the space of all possible actions for playing games. Does this have anything to do with engineering?
Yeah, it's dynamic programming.
It's dynamic programming.
Approximate.
And why does Google actually think there's any money in playing Go? What's their biggest cost? Apart from human labor? I mentioned it earlier. Energy. What if you viewed a large data center as a game, which you have about 160 knobs, I actually happen to know the number, which you can adjust, which will change the energy consumption of this system. Now you can do a stochastic gradient descent type method in the space of control states for your data center. You can get a 5% reduction in power. Yeah, you paid your salary for the next 100,000 years, right? So in fact, these are now used for actual commercial, within Google, for optimizing energy usage within data centers. So they're moving away from, cool, that's my face, that's my dog, that's my dog, that's so cool, to, can we save some energy, right? Real money. Obviously robotics, you can write kinematics, but it's hard to get all distinction pieces. These are widely used in robotics, plus at least all the robots at Penn are drones or cars, which need to have vision. Increasingly, people are using soft sensors. There are a lot of things that are hard to directly measure, like I'm making a polymer, what's its viscosity? What will the photodegradation look like a month from now? How much corrosion is inside this pipe? So you build non-linear models to try and estimate what the corrosion level might be within this pipe. So lots of nonlinear functions, certainly demand estimation, how much power will I need to produce tomorrow, so you decide if it's a coal or a cheaper piece is there, sales pieces there. Last quick case study, people have heard of Splunk? Some guy, a couple people. Interesting little startup company, IPO'd for $3 billion in 2012. Last I checked, it's about $8 billion market cap. I went to IBM and they're going, yeah, I know these guys. They stole $500 million of market share from us. Oh, that's interesting, what they do. What they collect is lots of data. And rather than building in a beautiful structured SQL database, they throw it in a big crappy piece here, where they're getting switches and safety routers and all sorts of information into a big machine learning piece, with not particularly sophisticated machine learning, but very nice way to store and compare this data, all of which, like much data you do with this time series data coming in. And they then build that so you can look at it, optimize it, see what's going on, make decisions, control your processes. And I think it's an interesting shift, again, going back to my opening statement. Classic engineering, in my opinion, is writing physics and chemistry models that describe the world, but an awful lot of running something like a power plant is knowing lots of stuff that's going on, where it's fairly hard to build a good model of what's driving demand, that's driving the amount of power you need to produce, or even understanding in theory, the physics behind a modern data center. In practice, no one has written a good model of energy consumption across a Google data center, right? In theory, you could write it and optimize it. In practice, it's easier just to optimize it. So I see this emerging paradigm with lots of collecting lots of information and sensors, which are often very flaky and miscalibrated and things, all feeding into big models, which then try, in the ideal world, be constrained in some way by physics, so they don't do stupid answers. And you notice I showed you a bunch of stupid examples, right? 90% super impressive, 10% or 1% really stupid. If you have something like an airplane or a power plant, you can't permit that. You have to either build a scaffold around it or build, a metaphorical scaffold, right? Safe region. You have to build some sort of physics in. But the trend is definitely to use much, much richer data sets of unknown physics to build your models, and then try to figure out how to make sure these things aren't going to kill you.
So how do you know that when you're wrong?
How do you know when you're wrong? With some things, it's not critical. If you're looking at corrosion, you try and spend the money and you take the pipe out and check it.
Let's talk about airplanes.
For the airplanes, now you're going to have to build some sort of a safety zone if you go outside. These things tend to be graded interpolation and crappy at extrapolation.
Okay.
It's a little tricky in a high dimensional space. In fact, it's high enough dimensional it's impossible to tell what's interpolated or extrapolated. But in some sense, they interpolate beautifully and they extrapolate who knows. And you need to know in some sense, am I extrapolating? And no, we don't know the answer. And no, I don't want my aircraft using these today. But you can imagine using these to optimize fuel consumption within your aircraft while still keeping the main control system untouched by them. And if they go outside of some safety region, the recommendation, you go, that would save energy, but we don't want to go down. So I don't know. This is why we all have jobs still, right? To figure these things out. So the takeaway, these things in some sense are just super flexible models, millions of parameters with lots of regularization, smoothing, dropout, squared error penalty, whatever you like. They really have changed machine vision, speech recognition, translation. Whole areas have been completely revolutionized. It's unclear how far they've penetrated in engineering. So all the companies I talk to are trying to hire people in this area as fast as they can, because they see this is a way to reduce energy costs, or makes it so I check for corrosion every 2 months instead of every month. You know, they're saving money building these models, so they want to hire you to do this sort of piece there. And really the philosophy is training by example. Try it out, see what happens, measure what goes in and out with very little programming and physics. On that thought, I will stop and thank you guys.
We have a few minutes again for questions, so we'll start with the students. If you have any questions, please.
Yeah.
So for examples that, like systems that you don't have much different examples, let's say minimizing energy, cannot really go to that data center, change the structure to see how energy is different. You have to have a model of.
So what do you do when you don't have much data? First of all, the energy center, you do have. This energy center has been running for 2 years, and it's all instrumented. Google's got great instrumentation. So they've been measuring exactly what the energy consumption is every minute for the last 2 years here. There's a lot of data. Now, what you don't know is which of that's correlation versus causality. It's got to be very careful. I like to point out that every time the heater's on, it's cold in the room. That's a causal model. You with me? Not the heater causing you to be cold, the cold can cause the heater to be on. But if you're careful with those, you can look at that historic data and still use it. And then what do? It's a stochastic gradient descent. You make a small little change. This has been done since the 80s that I can remember, and no doubt before that, as long as I can remember, in chemical plants. Since the 60s, where you do little changes in the plant, and you see whether it gets better or worse. But you do it combined with a model built over 2 years of minute-by-minute operation. So
I think it's actually what happens if it is a one-of-a-kind type system.
if something's, well, each data center is unique, and there's a different question, which is you've got 5 different plants. How do you generalize across them? That's a great area of research, which I do not have a good answer to. But I think all these things require lots of data, and the question of how do you generalize from one plant to another? Some things, there are lots of turbines that really are pretty much carbon copies of each other. You can go from one turbine to the next turbine for a bunch of them. It works quite well. You look at diagnosing is it about to fail based on the audio frequency of the okay. Whoop. So those things generalize pretty well. Other ones are in trouble. Yeah.
So is it possible to apply like machine learning neural networks to finding a good thermodynamics model?
There are a lot, I don't know if there's a dynamics model, there are a lot of people increasingly working on questions like material physics or material properties. So a standard question is, I want to design a polymer with some properties, or some lubricant with some properties, and there's clearly some nonlinear function between the chemical structure and the material physics properties. It's really hard to write down the physics to get the material properties from the chemical structure, but there is data there where you have lots of chemicals and lots of structures. That sort of stuff I've seen good work. I've never seen anybody doing thermo, so I'm not quite sure how you would do that. But I guess the question is, what's the input? Chemical structure, viscosity, photodegradation, color, whatever. Those ones you can collect data on.
We're not saying your PhD because of this.
Yeah. Don't give up your day job yet.
Anything else? I have a couple.
Okay.
The one is, if they can learn through data, why can we not?
Why can we not?
So we actually have to learn thermo, right? We cannot learn that
We
I don't
learn,
know,
we learn
Udacity
most,
will do
we
that.
learn, how do we learn? It's a great question. How do you learn to drive? You get a small amount of instruction, and currently these deep networks are terrible at taking instruction, so an active area is how do you take a human instruction of how to drive a car or to drive a plant, and convert that into instructions. That's an open active area. But a lot of it, once you get a little bit of driving, a lot of it is you try something and you say, whoa, that's a little wobbly, and you learn to not overcorrect.
Reinforcement learning.
It's a reinforcement learning. So we learn tons of things. How do you learn to recognize dogs and cats and alpacas? And the answer is, I don't know, and you don't know, because I work with psychologists who study these things. You do not know how you tell an alpaca from a cat. But a lot of our learning, and it's an interesting point, a lot of our learning does look very much like these vision systems. And a lot of it looks really different, right? How am I teaching you? By talking to you, not by giving you lots of training and feedback. And I think the successful systems in the long run will have both a mix of instruction. Here are some rules of what you can and can't do in this plant. Here's what I know about the physics, and a certain amount of exploratory rote memory, trying things out, seeing what happens. We really don't know how to do that now. There's a good 10 years of work there to try and get that done. That's, I think somewhere the right way is how do you build the right prior knowledge, physics, safety rules, whatever, into these incredible flexible models. I don't know how to do it. If I knew how to do that, well, I'd start a company.
Isn't it basically more examples?
No, I don't think it's just more examples. If you look at trying to train someone in thermodynamics, you do not train them just by showing them lots of examples of thermodynamics. You actually explain what entropy and enthalpy is. You give them formulas. We don't teach humans just by example.
You cannot learn the stick table, period.
Right? So I do think it is critical that we do learn as humans rules and approximate formulas, and often they're wrong because they neglect friction or other pieces of physics there, but they at least give a basis for which we can then adjust. I don't know really how to do that well here, but I think that's the right question.
My second question is, if I build a physics-based model for your Google data center,
Yep.
I'll come up with 200,000 keys and some variables in a T structure, discontinuous, this and that.
Yep.
So 3 days, 1 week to just do one simulation. Yours is going to be much faster.
Yep.
So what are we doing now?
I think the answer is many of the physics-based models have more apparent degrees of freedom than real degrees of freedom. And that if you were to find the most parsimonious form, you'd find something that's much simpler. Certainly when I look at the
Abstractions, essentially.
I'm trained in chemical engineering, and I look at these big chemical equation forms, and the ones I was fitting as a PhD student were so complicated, they were just like a neural net. There were lots of measurable freedoms, and there wasn't enough data to fit more than 4 or 5 degrees of freedom. We were fitting 400. We called them names that sounded like something coefficients, but I never really believed them. So I think the answer is that often we're building something because we know the components, but there is a simpler, the world sits in a low dimensional manifold or a subspace of this high dimensional space.
Cancel out.
Yeah, and so that pieces cancel out and project down, and that often one can summarize things in a much more condensed form, and these things, if you optimize in that direction, will find a lower dimensional representation. So it's a different way of thinking about it.
We're out of
Awesome.
time, so
Thank you.